Okay, what's up, crew? All right, so we're going over our test for tomorrow. We're talking about standard number 4. We're talking about the Earth and the Earth's atmosphere and its core. So, if you would, let's talk about this. When we talk about the Earth, we talk about tectonic plates and all that kind of stuff, plate tectonics. Let's talk about the 3 types of plate boundaries. First, you got divergent. So, divergent, going away, convergent, coming together, and transform. Be sure you can model all of these correctly and you can identify them on a map because you're going to be able to do that. Let's see, divergent, convergent, and transform. Next, what kind of geological events are created at each boundary? So in a divergent boundary, you get them separating like this. Any kind of boundary is always going to have earthquakes. So all 3 of these get earthquakes. But when you get the divergent plates happening, you get a seafloor forming. As the magma comes up and cools, you'll get a little bit of a ridge forming, all right, so spreading. Maybe some volcanoes as the magma comes up, forming kind of little islands and stuff. But for the most part, it's just going to be seafloor spreading at the bottom there with ridges. Over here with convergent, if you get 2 plates coming together, if they're both continental crusts, they will go up because they have equal density. If it's a continental crust coming together with an oceanic crust, the oceanic crust gets pushed down because it's more dense and it goes under. When it goes under, it drives magma up. And magma is able to rise into the continental plate, and it comes out in a big volcano. So that's how we get most of our traditional volcanoes that we think of with the giant explosions, driving the magma up as that tectonic plate goes down. And transform, that's the San Andreas fault, for example. That's where 2 plates are shifting by each other. And sometimes when they go by each other, sometimes they have little ridges, the hook, and they can't slide, they get stuck. And they build up energy until they snap. That's your tectonic plate boundary, and that won't have any volcanoes for any reason, really. It's really just primarily going to be the shifting of the plates and the tectonic, the earthquakes. Let me see, what's an island arc? So an island arc is formed when you have, under the ocean, you have maybe like a hot spot, some little source of reservoir of magma coming up. You can also have it formed when convergent boundaries come together, driving magma up. But the magma comes up and forms islands and just like a little arc. Think of Japan and the archipelago over there. All the different little islands all around each other. Formed from magma rising from a convergent boundary underneath. So a hot spot would be a magma chamber coming up in the middle of the plate as opposed to the edges. The edges would have the convergent, whereas a hot spot would be just somewhere in the middle of the plate. And a rift valley, that's where it spreads apart in a divergent boundary. So the rift valley forms in the bottom of the oceans usually. Model a subduction zone. So subduction zone, that's where you have the continental and the oceanic plate, and it comes down. So it's literally led down, driving the magma up, so it causes volcanoes. What is weathering? So break, move, drop. Weathering is the breaking, all right? What kinds of weathering are there? There's biological weathering, where we have a primary succession. You get plants landing on there, moss, lichen. They literally digest the rock and turn it into soil, and then plants die and they add humus to it, and it goes on from there, making soil. You also have chemical weathering. That's caused usually by us, where we're making toxic chemicals, sending them into the atmosphere, carbon dioxide and sulfur dioxide, and these things combine in the atmosphere to form to form sulfuric acid and carbonic acid, both of which will weather the rocks and break them down with the acid. And then you also have physical weathering, and that's usually where water gets into little cracks in the rock, and the water freezes, and water that freezes expands, and the expansion of that water breaks the rocks apart. That's the physical weathering there. How does weathering play a role in primary succession? Because remember, biological weathering, and even physical weathering and chemical. You have to take that top layer of rock and break it down for soil to be formed, because soil is made up of the individual rock particles, the sediment. So you have to have someone breaking that stuff down first to start off primary succession. Model and label the different soil horizons and give a description of the composition of each. So if we talk about our soil horizons, we have the O for the organic layer, or the 0 layer. And we have our A, we have our B, and we have our C. So we have our top soil layer, tons of humus, right, all that good stuff. Here we still have a lot of organic material, all right, and mixed in with some traditional sand or clay or silt. B, you get kind of broken up bedrock, right, but it's still got some solid rock in here. And C would just be the straight bedrock that forms the deep layer. Because again, as you add layers on top, you get more pressure and it forces it into forming a more solid rock form. Let me see. Where is the most organic material in the soil? That's in the top layer, in the O horizon, and the humus. What are the 3 base types of soil? That's your sand, silt, and clay. Rank them in terms of water retention. Well, if you remember the lab we did over there, if you got a whole lot of clay, then it's not going to let a lot of water through. If you got a whole lot of sand, it's just going to go straight through. That's because the sand particles are so big. There's a lot of gaps through them because they're just too big and the water moves through them easily. The clay is much smaller and finer, and as a result, the water can't get through as easily. There aren't as many holes for it to move down. Let's see, what is permeability? Permeability is its ability to be permeated, to make holes. So its ability to pass through. So sand would have a high permeability and clay would have a low permeability. What's the most permeable soil? Well, we talked about that, sand. Which soil is best for water retention? I don't know why I asked this question again, but that's okay. That would be anything with clay and silt. Which would be best for growing plants? We talked about this. This is the sandy loam, all right? Some kind of loam. It's usually considered to be an even mixture of all 3 types. So 30%, or I should say 33% clay, 33% silt, and 33% sand. Somewhere around there is going to be your best soil, a mixture of all of them. Why should you test for nitrogen, potash, phosphorus, and pH in the soil? Nitrogen, phosphorus, and potassium are all essential elements in the growth of organisms. So plants need them. And we know about the nitrogen cycle and the phosphorus cycle, but you test for them because they need those in order to grow and make new plants. So pH, though, is important because that's acidity. So if your oil is too acidic, it could be bad for the plant. If it's too basic, it's bad for the plant. In fact, some plants like to have acid soil. Some plants like to have basic or alkaline soil. It just depends on the plant. So it's important to know that before you start planting things. Or you end up with like the trees we have in our yards. I don't know if it's a pH thing or if it's a water retention thing, but the trees are really struggling. You can see around the school. Keeping this going. So this is our triangle, the soil triangle. Remember how it works? If you're given percents, like let's say, I think we actually have some examples here a little bit lower. Do I have some examples? No, I do not. So let's say that we have 40% sand, we have 20% silt, and we'll say 20% clay. I think that's right. So we have 20% clay. So we'll come over here, we'll start with the clay, 20%, right? And then we will move to the right for the percent silt. So we move to the right and find that line for silt 20, and it crosses right here. And then we have the sand, which is at 40%, and that's up here. So we got here. What am I doing wrong? Sand, clay, and silt. Oh, that's what I'm doing wrong. Okay, let's try this again. Ignore everything I just said, and let's try this again. I cannot add to 100 apparently. So we'll do 40, 40, 20. That's what was going wrong. So we have, let me see, 40% sand, so I found my 40. And remember, it goes in this order. Here, here, and here. That's the direction that these lines travel. So we do 40% from sand. Sand's down here, so 40 for sand. Sand goes up like this. We have 40% silt. Silt's here, and it goes down like this. And then we have 20% clay. Clay moves to the right. And you see, there we go. It crosses right here in the loam. And that's how you find the type of soil. Okay, so remember, to the right, down to the left, and up to the left. Okay, that's how this should work. Let's try some new values here. So let's do 10. We'll do 80 and 10. How about that? So let's start over here. Let's start with percent clay because it's a little bit easier to start with. So clay, we'll do 10%. That's moving to the right. Please work. Thank you. Then we have silt. That's 80%. That's right here. Moving down. And then we have sand, which is down here, moving up. And so that would be a mixture of silt and silt loam, obviously, because it's got a lot of silt in it, as opposed to this would have a lot of sand. So that's another way you can kind of check it out, and then you have clay up here. This stuff right here in the middle, usually around 50% for each, is usually kind of what, or excuse me, 30% for each is kind of what you want to find. 30, 30, 30, somewhere in this range of some kind of loam, sandy loam, or whatever, okay? All right, moving on down. Let me see. So this right here are the percents in the Earth's atmosphere. So we see that the predominant gas in the Earth's atmosphere is nitrogen at about 78%. Oxygen is about 20%, 21%. And then the rest is all trace. All right, nitrogen, we have oxygen here, and then we have these trace elements. So argon, 0.93%. Xenon, 0.00009. Neon, 0.018. Hydrogen, 0.005. And this is the one most of you might know about, which is 0.04%. 0.04% of our atmosphere is carbon dioxide, which doesn't seem like a lot. But you got to remember how many atoms are in one speck of dust and how many atoms there are, therefore, in the entire Earth's atmosphere. That's a large number. Keeping it going. What are the layers of the atmosphere? Ooh, TSMT's the order. So we have the troposphere, stratosphere, mesosphere, and thermosphere. Those are the layers of the Earth's atmosphere. Which one has the most mass, the most stuff in it? That would be our troposphere, right? And that's because when we talk about the Earth pulls the atmosphere to it with gravity. So the more intense the gravity, the closer you are to the Earth, the more gases you're going to have stored there. So most of the gas is close to the Earth in the troposphere. All right, it's Earth's thickest layer in terms of the actual particles in here. It's the thinnest layer in terms of actual thickness, like how far it is from the Earth's surface to the top of the troposphere. And then it hits this layer called the tropopause. I don't know if I mentioned this before or not, but it should be pretty clear. Tropopause is the layer, or the pause between the troposphere and the one above, which would be the stratosphere. So stratosphere is a little bit bigger, all right? And in the stratosphere here, we have our very important layer of ozone. Ozone, better known as O3. Okay, it absorbs UV radiation. And this is very, very key. The ozone layer absorbs UV radiation, creating a little bit of heat. So even though the temperature as you go up should go down, the stratosphere actually gets a little bit warmer because it's absorbing UV radiation using the ozone layer in the stratosphere. Now, in absorbing that UV radiation, there's a problem because we have been making chemicals that was destroying the UV protection here by destroying the ozone. And those were CFCs, chlorofluorocarbons, CFCs. CFCs break apart ozone and prevent it from doing what it's supposed to do. So since it can't do what it's supposed to do, it doesn't protect us from UV rays, and we were having a serious issue with skin cancer problems, which I know we still are, but it was certainly not helping it out. Okay, so that was going on inside the stratosphere. People oftentimes get the CFCs confused with global warming. Just keep in mind, global warming is more about the carbon dioxide, and the stratosphere has to do more with ozone and CFCs. Which one has the most water? Well, the one with the most atoms, so that would be the troposphere. All right, which one has the most weather? Again, the troposphere. If you got lots of water in the air, then you're going to have lots of weather, lots of rain, lots of storms. Rain, water causes weather. That's very important for what we got coming up soon. So without rain, you wouldn't have the weather. Continuing, which one contains the ozone layer? So that would be the stratosphere we just talked about. What's the ozone layer for? Protecting from UV radiation. Which layer is the hottest? That is going to be our thermosphere. All right, or if you look down here, the exosphere, although some people don't consider that to be an actual sphere of the Earth because it just means the outer layer. But these layers are rather hot the higher you go up because they are exposed to intense amount of solar radiation. All right, and all those gamma rays and those X-rays, all right, they hit that layer and heat that the little bits of gas that are up there, they heat up extensively. So it has a really high temperature, which is why we call it the thermosphere. But moving on back down to here, if we're looking to look, troposphere, as it goes up in height, goes down in temperature like it should. Stratosphere, you can see that about right here starts the ozone layer. So these things pick up energy as it goes up in the stratosphere because you're absorbing the UV radiation. In the mesosphere, there's not too much that goes on there, so the temperature goes back down. It does, however, stop any all meteors. And I know that because the mesosphere starts with me and meteors start with me. That's how I remember that. Keep it going to the thermosphere. So again, very little atmosphere up here, almost none, all right? But in the thermosphere, you are picking up solar radiation and creating the auroras, Aurora Borealis and the Aurora Australis. And they happen all the way up here and actually they show that the sun is trying to kill us with gamma rays because that's where the actual air is absorbing those rays and releasing it as light in different colors. That's the aurora up there, okay? And then the exosphere is the outer layer of the atmosphere. But again, very little actual air up there. So we know why there's an increase in temperature up there. We know where it burns up the atmosphere or burns up meteors. What is the root cause of the wind patterns on Earth? So all wind, all motion of any kind usually requires some kind of convection current. All right, the movement of the air particles there is convection, and that requires a source of heat. So that would be the sun, or insolation. Insolation. Sol being our star, the sun. Okay. Describe and model how convection works. Hot things go up, and then they push these out the way, and as they push them out the way, they cool and they descend because they're more dense. And then as this stuff goes up, it creates a vacuum, and so it pulls in the cooler air, heats it back up, and sends it back up. So you got heat driving stuff up, making it less dense, moving out of the way of the incoming air, coming down because it's cooling, and then being sucked back air into the space, and then being sent back up through heat. All right. What is a Hadley cell? Hadley cells are these little convection currents in the Earth's atmosphere. Polar cells, Hadley cells, and I forget what the other specific name was. But there's about 3 per hemisphere. Now, how does Coriolis effect play a role? Well, if there were no Coriolis effect, you would only have one convection current, right? The hot air traveling towards the colder regions, the colder regions sending the cold air back down towards the equator. Just one. But because the Earth is spinning from left to right, because it's spinning, it makes these kind of divide up. Because the air at the equator is traveling way faster than the air up here at the poles, because it's got a greater distance to go around. That's the Coriolis effect, the different speeds at the equator versus at the poles. And that causes the breakup of that one giant convection current into 3 separate convection currents. How do Hadley cells contribute to biomes? Well, if you have lots of air going up at the equator, that is air that's hot. It's got lots of moisture in it because it's hot and it evaporates with the water. So there's tons of rain around the equator because of the moisture in that air. But as it moves over here, it loses that moisture, and when it finally comes back down, it's completely dry. So where it comes back down, that's where the deserts are, because it's now dried out. Which areas of Earth receive indirect sunlight? Those would be the poles, because they're pointed away. Like when I shined that light at you guys and you turned your heads away, so it was indirect light reaching your eyes. It's the same thing up here. At the poles, it's going to reach indirectly because they're kind of tilted away, as opposed to the equator, which is kind of straight on. Why do seasons exist? Seasons only exist because the Earth is tilted, and as it goes around the Earth, these seasons change, all right, because of the Earth's tilt. So if you remember, when we were sending the Earth here around the sun, it was always pointing the same way with the same tilt, and just different areas were facing the sun with summer, and then some of them were facing away in winter. And depending on the side, you would be either summer or winter, right? On which part you are around. And then your springs and your autumns. Okay? All right, let me see here. Oh, if there was no tilt, there would be no seasons. All you would have an Earth where it's always cold up here, it's always cold down here, and in between it's always nice and warm. Really hot at the equator, and then pretty average temperatures year round in certain areas of the world. So because of the tilt, we have to deal with seasons. If there was no tilt, we would have no seasons. We just have, a great place to live all year round. Now, model winter in the northern hemisphere. So if I'm modeling winter, I got the sun, I need the Earth, I need to draw the equator here. Ooh, excuse me. The North Pole, South Pole. Excuse me. This says model winter. Unfortunately, here I've drawn a model of summer because the north is leaning to it. So I want the north not leaning towards, I want the north leaning away. And that would cause winter in the northern hemisphere. Okay? How much daylight does the South Pole get when the northern hemisphere is experiencing winter? So if you look at our little Earth here, you might notice that that the South Pole is actually pretty much always facing towards, always facing towards the sun. And if it's always facing towards the sun, why am I doing this wrong? If it's always facing towards the sun, it's always going to be bright. So you will get 24 hours of daylight here, whereas the sunlight can't reach the North Pole up there. It would be 24 hours of darkness. And it's caused by the tilt of that Earth. What's insolation energy? That is the energy from the sun. What happens on the winter solstice? That is the shortest day of the year, on December 21st. All right. What happens on the summer solstice? Well, the summer solstice will be the opposite of that. When it's the longest day of the year, that is on June 21st. What happens on the autumnal and vernal equinoxes? Well, equinox means equal night. So, during the autumn, September 21st. And then during the vernal equinox, which is March 21st. Those are the specific days where you have equal days and equal nights in specific places of the world. I guess probably for us in the U.S., those would be the days. Now, how can mountains affect the climate of the Earth? Excuse me. So if you remember, you have the Himalayan mountains formed when India catapulted itself straight into Asia and caused these gigantic mountains to form, the Himalayan mountains, with the convergent plates there. And when they did, these mountains, the Himalayas, prevent clouds of rain from making their way into the Gobi Desert. And that's why it is a desert. Okay, and then you have all this rain over here, and you have monsoons all the time in India because these mountains block the passage of that rain. They're so tall. So it creates the Gobi Desert behind it. This is called a rain shadow. So it's raining over here, and then there's like literally a shadow of desert non-rain over here. Excuse me, like a shadow, you have light, and then you have the shadow. So light has tons of light, the shadow doesn't. The rain over here is tons of rain, and then there's a rain shadow where there's very little rain. Excuse me. Well, how can oceans affect the climate on the Earth? Well, the ocean currents, sometimes they can heat up certain areas of the world, like Ireland and England, which should be nice and cold, or even Seattle, which should be nice and cold, and keep it warm all year round. And that's because the ocean currents carry some heat up there and release it into the atmosphere. What is El Nino? Describe and model. So El Nino, if I can find my specific thing here. Here we go. El Nino is simply this. When you have this Pacific jet stream coming across, okay, and it's basically just some nice warm air here. I don't know why this isn't that. Oh, I should zoom out a little bit to get the La Nina in there. Okay, so with El Nino, you start by having really warm water coming across over here, excuse me, towards the southern United States. And what happens is all that warm air actually causes a, I don't know how best to say this, causes a changing in the polar jet stream up here. And that changing in the polar jet stream, well, I'll tell you what, let's just do this. I'm going to go over this with you tomorrow. It's 4:10, I need to get on to go see my son. This is the last thing on here. I'll go over this in detail with you tomorrow in class before we move on and then test on it. Because I want to make sure that I'm not saying anything wrong, because I probably need to go over this again. So I'll go over this for you tomorrow, okay? So these are the last two things that I had on there for you. Yeah. So these are the models if you wanted to investigate, and you can always watch some videos online for tomorrow, but I'll go through that more with you later, okay? All right. Happy Halloween, guys. I'll see y'all tomorrow. Study. Do your, what are they called? Practice tests when you find time. Bye.